Everybody, welcome back. We're going to talk this session about equilibrium constants, which is section 9.8 from your textbook. So an equilibrium constant is a numerical value that characterizes the relationship between the concentrations of reactants and products in a system that's reached chemical equilibrium. So to review from last time, a system has reached equilibrium when the concentration, shown here on the y-axis, of the reactants and the products is no longer changing. So shown in red for the following chemical reaction, H2 plus I2 makes 2HI. Shown in red is the concentrations of the reactants, H2 and I2. So in a chemical equilibrium reaction, at the beginning of the reaction, you have a high concentration of reactants. You're just mixing these two together, so there's lots of them present. But as H2 and I2 are converted into the product, HI, the concentrations of H2 and I2 decreases, which is shown here. As that is happening, product is being made. So eventually, well, initially, your product concentration is 0. You don't have any product at the start of the reaction. You have to make it first. But as product is made, its concentration goes up. Eventually, because this is an equilibrium reaction, every time reactants come together to make product, product will also revert back to reactants. And so the rates will be equal. The rate of the forward reaction will equal the rate of the reverse reaction. And so when that happens, every time you make product and the concentration goes up a little bit, some of that product is reverted back into reactants. And so eventually what happens is the concentration of your products and the concentration of your reactants no longer changes. And when the concentrations of your products and your reactants stop changing, they reach this steady state or flat line, that's when chemical equilibrium has been reached. So this dotted line here shows the point at which equilibrium has been established. So we can mathematically relate these concentrations, the concentrations of product and the concentrations of reactants, using an equilibrium constant. So we abbreviate the equilibrium constant KEQ to show the relationship between the concentrations of products and the concentrations of reactants in a chemical equilibrium reaction. So the equilibrium constant KEQ is obtained by writing what we call an equilibrium constant expression, and then we evaluate it numerically, plugging in values. So let's say we have a chemical reaction where we have reactant A reacting with reactant B to make reactant C, or product C and product D. And shown in front here are the coefficients for this chemical reaction once it's been balanced. So let's just point this out. These are the coefficients. And then these are your reactants, A and B, and your products are C and D with their balanced coefficients in front. Just going to get rid of that so we can see it better. So the equilibrium constant expression for the above reaction is going to relate the concentration of the products and the reactants as a ratio. And so what it will look like is KEQ is generally written as the concentration of all the products, and these square brackets mean concentration in terms of molarity. So the molarity of each product produced raised to the power of its coefficient from the balanced chemical equation. And you do this for each product and multiply them together. So for this reaction up here, where our products are C and D, and their coefficients are Y and Z, we take the concentration of product C and molarity and raise it to the power of its coefficient Y. And for D, our other product, we take the concentration of product D and raise it to its coefficient Z. And we divide that by the same process for the reactant. So we take each reactant, reactant A, its concentration, which is what those square brackets mean, raised to the power W, the coefficient from the balanced chemical equation. And we take the concentration of reactant B, raised to the power of its coefficient from the balanced chemical equation. And the ratio of the concentration of the products raised to their coefficients divided by the concentration of the reactants raised to their coefficients equals KEQ. And what this tells us is essentially if KEQ is really high, it's a value significantly larger than 1, what that means, if KEQ significantly larger than 1, it means that the top part of this fraction is a large number. So it means that we have a really high concentration of products if KEQ is significantly higher than 1, because the ratio of products to reactants is significantly bigger than 1, which means the top part of this fraction has to be a large number, significantly greater than 1. And if KEQ is significantly less than 1, what that means is the ratio of the concentrations of the products over the reactants is relatively small. It's a decimal value less than 1. So that means the concentration of products is low and the concentration of reactants is high. If the concentration of products is low and the concentration of reactants is high once equilibrium is established, that means that not very much of the reactants were converted into products. Most of the reactants were, if they were converted into products, they got quickly converted back into reactants to have a high concentration of reactants. So the equilibrium reaction favored the reactants because their concentration stayed high. If KEQ was larger than 1, significantly greater than 1, again, that means the concentration of products is high and the reactants concentration is low, because for this ratio to be greater than 1, the value on the top, the numerator needs to be a larger number than the denominator. So if the concentration of products is high, that means the reaction favored the forward direction to make lots of the products. So by evaluating equilibrium expressions for KEQ, when we look at the value of KEQ, we can get a sense of, did the reaction favor producing products? Was it pushed to the right to make more product? Or did it favor the reverse reaction, making reactants? And again, if KEQ is significantly larger than 1, that means the concentration of products was relatively high compared to the concentration of reactants, and the forward reaction was preferred or favored. And if KEQ is low, significantly less than 1, it's the opposite. It means that you had a lot of reactants, their concentration was very high compared to products, and so the reverse reaction was favored. So analyzing for KEQ, computing KEQ, can give you an idea of, with a chemical reaction, once it's reached equilibrium, do you expect to make a lot of product, or are most of your reactants going to stay as reactants? Some notes on writing equilibrium constants. The square brackets in the equilibrium constant expression refer to the molar concentration, the concentration of the reactants and products in moles per liter, or molarity. When you're writing a KEQ expression, it's always products over reactants. So the products are always going to go on top of the ratio in the numerator, and it's the concentration of each product raised to the power of its coefficient from the balanced chemical equation, and then you multiply that for all the products together on the top of this equation. The reactants are always going to go on the bottom in the denominator, and it's the molar concentration of each reactant, the molarity, raised to its coefficient from the balanced chemical equation, and each reactant is multiplied together on the bottom. When you write KEQ expressions, you only want to include substances that are gases or that are in aqueous solution. So in your chemical reaction, when you look at the phases, if anything is gas or AQ, you can put it in the KEQ expression. But if you have a solid or a liquid, it can't go in the KEQ expression. Do not include. And then again, the coefficients from the balanced chemical equation are used to determine the power, the exponent that each concentration is raised to. So in this general form of the equation I wrote, it's always the concentration of each product raised to the power of its coefficient from the balanced chemical equation, and you multiply that together for each product. And then on the bottom, it's always reactants raised to the power of their coefficient from the balanced chemical equation. So again, only concentrations of substances that are in solution, that are in the aqueous phase, or substances that are gases are going to be included in the expression for KEQ. So pure solids and pure liquids, such as water when it's in a pure liquid state, are not included in the expressions for an equilibrium constant. The reason for this is that pure substances, like a pure solid or pure water, they have a constant concentration. So we don't have to include them in the expression for KEQ. Because they're not mixed into the solution, their concentration won't be changing as we add more of them to the solution as they're produced in the chemical reaction, or as we remove them from the solution as they're used up in a chemical reaction. So only things that are gases or aqueous are included in KEQ expressions, and pure substances like solids and pure liquids are not included. So if water is in the liquid state, you don't include it. But if water is in the gas state, you have water vapor in your chemical reaction, or you're producing water gas, then you would include it in the KEQ expression. And so just for example, pure water has a concentration of 55.5 moles per liter, 55.5 molar. And this doesn't change if you change the volume of the water. So like 10 milliliters of water has a concentration of 55.5 molar, and 1,000,000 milliliters of water still has a concentration of 55.5 molar. Because it's a pure substance, its concentration doesn't change. So to write an expression for an equilibrium constant, you only need a balanced chemical equation. And just from a balanced chemical equation, you can write the expression. So for this equation where you have ammonia gas reacting with oxygen gas to make ammonia, to make nitrogen dioxide and water, we check everything's in the gas state. So everything will be included in the equilibrium expression. If water here was in the liquid state, it wouldn't be included. So to write this equilibrium expression, you want to take the concentration of each of the products raised to its coefficient from the balanced chemical equation. So our product, nitrogen dioxide, raised to the fourth because it has a 4 here. And our concentration of water raised to the 6 because it has a 6 coefficient here. And then on the bottom goes the concentrations of each of our reactants raised to the power of their coefficient. So we have ammonia raised to the 4th from its coefficient 4. And we have oxygen gas raised to the 7th because of its coefficient 7 in the chemical equation. And so then a typical problem, and we'll do an example at the end, would be you're given a chemical equation, you're given the concentrations of products and reactants, and you write the expression, and then you plug in the given concentrations to calculate KEQ. Another common type of problem is you might be given KEQ, and you're given the concentration of everything in the chemical reaction except one thing, and you might be then asked to solve for the concentration of O2. It's a little bit harder math, but it's going to be one of those two types of problems. On the quiz this week, you should expect to solve a problem where you're given an equilibrium expression, you're given the equation, you have to write the expression, and then you have to plug in the concentrations and solve for KEQ. And again, we include water in this one because it's a gas, but if it were a pure liquid, it wouldn't be included in the KEQ expression. So equilibrium constants can give us an indication of the reaction completeness or kind of the position of the equilibrium. And so if your value of KEQ is very large, more than 10 to the 30th, what that means is that essentially that reaction produced all products. And we'd say that the equilibrium position is shifted far to the right. It means that in this chemical reaction, nearly 100% of the reactants were converted to products, and there was very, very little of the reverse reaction happening. And so even though it's technically an equilibrium reaction, it's essentially a one-way reaction because so little product was reverted back into reactants. The equilibrium favored the product side immensely. So we say that's shifted far to the right to show that the reaction favors products, which is the arrow that points to the right. If you have a KEQ value that's large, but not super high, so about 10 to the 10th, then we say that the value of KEQ is large and that you have more products than reactants. And so we shifted to the right, but you wouldn't necessarily say it's far to the right. So products were favored over reactants still, but not as much as when you have a KEQ that's this large. If your KEQ is near 1, and by near 1, we mean anywhere between 1,000 to 0.001, then this means you have significant amounts of both products and reactants, and your equilibrium position isn't shifted to the left or to the right. It's about equal. So you have about an equal conversion of reactants to products and products back to reactants. If you have a small KEQ, about 10 to the negative 10th, then you have more reactants than products, a higher concentration of reactants compared to products. So the description of the equilibrium position is to the left. It means that, yes, some reactants were converted into products, but there's a higher concentration of reactants left at the end of the reaction, meaning that if reactants were converted to products, they were reverted back into reactants to keep the reactant concentration relatively high compared to the product concentration. And if KEQ is very, very, very small, less than 10 to the negative 30th, essentially you have all reactants. So we say that the equilibrium position is shifted far to the left. This means that essentially you didn't get any reaction. Very, very little of the reactants were converted into products. So when you plugged in your KEQ expression, your product concentrations on top were very, very small. And your reactant concentrations on the bottom were very, very large. So when you divided this ratio, a small number divided by a very, very, very large number gives you a very small number, a decimal value 10 to the negative 30th or so. And we say that position is shifted far to the left. Essentially, no reaction happened. So let's do an example. Let's calculate KEQ for the reaction below. If our concentration of nitrogen gas is 0.0013 molar, our concentration of oxygen gas is 0.0024 molar, and our concentration of nitrogen dioxide is 0.0065 molar. And then let's describe the equilibrium position of this reaction based on our calculated KEQ. So first thing, let's set up our equilibrium expression. So KEQ is going to be the concentration of our products. In this case, we just have one product raised to its coefficient. So it's going to be our concentration of NO2 raised to the second, divided by the concentrations of each of our reactants raised to their coefficient and multiplied together. So divided by the concentration of N2. And there's no coefficient in front of here, so it's just raised to the 1 or just the concentration of N2. Times the concentration of O2, our other reactant. And it has a coefficient of 2, so we're going to raise that concentration to the power of 2 or square it. So when I plug this into my calculator, I'm going to do NO2 concentration on top, 0.0065 molar raised to the second, divided by concentration of nitrogen, 0.0013. And that doesn't have to be raised to anything because it has a coefficient of 1 in front of it, times my concentration of oxygen, 0.0024 molar. And that needs to be raised to the second because there's a coefficient of 2 in front of oxygen. Raised to the second, put that whole thing in parentheses. You plug it into your calculator. I did this earlier, but I want to double check my work, triple check it. So 0.0065 raised to the second divided by 0.0013 times, in parentheses, because I want to make sure that the second is applied just to the concentration of oxygen. I'm going to put this in parentheses in my calculator to make sure I don't make a calculator mistake. But I'm going to multiply the 0.0013 times 0.0024 raised to the second. I'm just checking my work here. And I'm checking my work because I ended up getting 2 different answers both times I got it. So let me do it one more time. Wait. So I got 5642.36. And we would want to round this to 2 sig figs, since we have 2 sig figs in each of our given values. So 5.6 times 10 to the third. So if we go back a slide, and we can't see it very well, but we check that this is considered a large between a near 1 and a large KEQ. So our equilibrium is shifted to the right. KEQ is greater than 1. It's about 5,600. So we'd say that the equilibrium position is shifted to the right to favor making products. Shifted right, products favored. And that's again because KEQ is greater than 1. Okay, so that's an example of calculating KEQ. Make sure you know how to do that for the quiz this week, so you can answer this type of question on quizzes and exams. Okay, we'll talk more about equilibrium, ways to shift equilibrium left or right by changing the reaction conditions in our next lecture. Thanks for listening. Bye.